Hello everybody. My name is Love Sasdeva and I'm a student in VIT Chennai. So, today what we are going to study is RSA Cryptosystem. It is a subtopic of blockchain and technology. So, let's begin with it. So, first we have to review the security key cryptography. Which is basically since RSA is a cryptographic technique, which is a digital signature kind of technique to verify the authenticity of the message. So first we will review the secret key cryptography, that what the basics of the technology is. Then we will proceed on to the main topic. Let's see. The confidentiality. The confidentiality is one characteristic of a cryptographic technique. So it has to be confidential. We don't have to share the keys and all. We just have a public key and a private key. So we share the public key and we secure the private key. So that is confidentiality. Integrity. Since these are the crypto hash functions, so it maintains the integrity because it is very hard to crack. So the limitation: sender and receiver must share the same key. So one limitation is then one key we have to keep the same, like public key should be the same key. So that is the main limitation of the cryptographic technique. So impossible for two parties to have a prior relationship, needs many keys for n parties to communicate. So there's that. So once each party has a pair of k minus 1 keys. So k is the public key and used for encryption, k minus 1 is the private key and used for decryption. We will see these topics. So this is the basic relationship which we have to satisfy. So we will see to this in depth. So knowing the public key k, it is computationally infeasible to compute the private key k minus 1. How to check k minus 1 is a pair? Offers only computational security. PK encryption impossible when p is equal to np, as deriving k minus 1 is not possible. So basically, since these are crypto hash functions, and the basic property of a crypto hash function is that they are very unlikely to get cracked because of the computational limitations of the current systems. One has to find the exact solution of the hash function, or some basically some crypto functions, almost all hash functions can be found a solution. So but it is infeasible to find. So basically the hash function are infeasible to find. That's why it is not possible to match the key pair. So if one goes to see the pair, it has to spend around 10 to the power 27 years to crack it. So that is the basic property of a hash function. So the public key k may be publicly available in a publicly available directory. Many can encrypt, only one can decrypt. So the one who can decrypt has the private key. So public key systems, aka asymmetric crypto systems. So public key cryptography, early history, we have to see the history and all. So the concept is proposed in Diffie and Hellman, new decades. It is basic old school stuff to go to the public history of the cryptography. So that is that. It is not much required. It has just who built it and everything. So the public key encryption was proposed in 1970 by James Ellis. So in a classifier paper made public in 1997 by the British Government Communications Headquarters. Concept of digital signature is still originally due to Diffie and Hellman. So the public key algorithm. Let's see it through the types of algorithms in public key encryption. Almost all public key algorithms use number theory or modular arithmetic or elliptical curves. So the RSA, which we are going to see today, is the RSA crypto systems based on the hardness of the factoring large numbers. So we will see to this in future in detail. So the other technique which we are not going to see is Elgamal technique. So based on the hardness of the problem solving discrete logarithm, it basically does the log and mod to encrypt and decrypt. It uses the mod function to encrypt the hash function with a number which is infeasible to solve, and then we use the log and mod function together to decrypt with the help of the private key of the network. But RSA is a totally different algorithm, as we will see. So what is RSA algorithm? RSA algorithm was invented in 1978 by Ron Rivest, Adi Shamir and Leonard Alderman. So it was published by this paper. So security relies on the difficulty of factoring large composite numbers. Essentially, the same algorithm was discovered in 1973 by Claude Clocks, who works for the British. Just so you know. So let's move to the next topic, which is RSA public key crypto system. So the first of this topic is how the keys are generated in the system. So the keys are generated by the following method. So we have to select two large prime numbers of about same size, P and Q. The basic is the GCD, the greatest common factor of those two numbers, should be 1. So it will be co-prime. So we have to select two large prime numbers which will obviously be co-prime of about the same size, P and Q. Typically each P and Q has 512 and 2048 bits. So these bits have to be long to encrypt the hash function so that it is infeasible to solve. So it has to be 512 and 2048 bits. So then we have to compute n is equal to pq and phi n is equal to q minus 1 p minus 1. So this is basically to encrypt and generate the key. So then we have to select e, which should be between the range 1 to phi of n. The phi of n is the function which we did just here, q minus 1 and p minus 1, and the two numbers p and q are the number which we have to use to find keys. So these can be any two random numbers. It's just that the greatest common factor of those numbers should be 1. So that is the one sole thing we have to keep in mind. So then we will select e between the function p minus 1 q minus 1 of phi n and the range 1. So any number between this should be this. So then we have to find the GCD e and phi n, which is also should be 1. So typically e is equal to 3 and e is equal to 65537. So this is the basically range of the functions. So then we have to compute d, which is again 1, and phi, which is between the range 1 and phi n. So then we will do ed is equal to 1 mod phi of n. Knowing phi n, d should be easy to compute, and without knowing d, it should be infeasible to compute. So hence we will find out two keys, which is e, n, and the private key d. So this is the basics of how the key is generated. The two keys which are generated are how. So one of them is a public key. It can be e or n, anybody, and one will be the private key. The other one will be the private key. Oh, sorry. Sorry for the mistake. The public key should be e, n, and the private key can be d. So these are the two keys which we have to compute. The only thing we have to keep in mind is the keys should be between the range to 1 and phi n. So these are the two conditions. Just one condition we have to keep in mind. So moving on, we have to see the RSA description. So encryption and decryption we will see in this topic. After the keys are generated, we will try to encrypt and then we will subsequently try to decrypt the function. So the formula for that is given a message m, so it will be between the range 0 to n. N is a normal range. So then m belongs to the integer function minus the phi. So use of public key, e and n, which were the public keys which we generated by that function. So we will use these keys, public keys, it will be in the database. We will use that keys to compute c, which is equal to m, the given message, to the power e and mod n. So this is how we will encrypt the function. The hash function which will be generated by a random number n, by modulo dividing with a random number n, will give us the encrypted message. Now to decrypt that message, what we have to use is we have to use the private key d. The person only who has the private key can decrypt the RSA decryption. So given a ciphertext c, used private key, given a ciphertext c, use private key d. So compute cd mod n is equal to m to the power e mod n, which is the c function. So which is the function which we use to the message we use to encrypt. So the encrypted message raised to the power d, which is the private key, mod n, the number which was chosen to encrypt the message. So mod n will give us the final message m. So as we have seen in this, the system generated two keys e and n. Both were used. These were the public keys. Both keys were used to encrypt the message by the function m to the power e mod n, which is the public keys. So after the message is encrypted, the other thing which we have to do is to decrypt. Obviously, if a sender sends a message, the receiver should be able to decrypt to be able to process it. So then we have the way to decrypt is the encrypted message we will take raised to the power the private key mod n. So as we can see here, so m to the power e mod n, which is the encrypted message d mod n. So this will give us the message back. So as we can already see, the person who has the private key can only decrypt. So as these concepts are clear, we will move forward. So yeah, we can see this through a diagram also. We will use a plain text m as I said to you, and then we will use a message to the encrypted message c is equal to me mod n, which was generated by the two keys e and n, and then we will try to decrypt the message using the encrypted message modulus into the power the message we use in the private key divided by n. So this will give us a remainder. The remainder will be the message. So from n, it is difficult to find out p. It is actually infeasible to find. It is difficult as well as it is infeasible. Like if somebody tries to decrypt it, it will take us a very long time, because all are hash function and we have to use the value one by one every value to check if it is mod n is equal to the message. So it is very infeasible to decrypt. Also the public keys e and n are difficult to figure, very difficult to find out the private key, which is d. So from n and e and c, difficult to figure out message m stc is equal to m to power e. So let's take an example of the RSA crypto system. So as we can see, the one public key is p and the other is q, and n is equal to 77. N is the number used to mod. So the phi n, which is p minus 1 into q minus 1, will come out to 60. 11 minus 1 10, 7 minus 1 6, 10 into 6 60. So this is the phi n function. The range should be the range of the keys should be equal, should be between 1 and the phi n. So let's choose two random numbers, which are d, which is the obviously the private key, and e is equal to 37. So once we find ED, so it will come to 481, and when we will mod it by 60, which is the phi n function, it would be 1. So let m is equal to 15, and then the message should be 15. The message is 15. So then the encrypted message will be m to the power e mod n. So 15 to the power 37, which is the public key, mod n. N is the other public key, mod 77. It gives us 71. So now if we have to decrypt it, what we have to do is we have to use the formula, the encrypted message, which is c raised to the power the private key d mod n, which is the public key. So as we can see, when we use this formula, the 71 raised to the power 13, which is the decrypt private key, mod the public key, which is 77n, it gives us 15. It returns the message back. So it basically decrypts the message. So this is one example. We can see another example also. So the p here is the random numbers p and q. Here are 3 and 5. So the pq raised pq becomes 15, and if we find the phi n function, which is p minus 1 into q minus 1, it will give us 3 minus 1 into 5 minus 1, which is 2 into 4. So the function which we got is phi n is equal to 8. So if e is equal to 3, then what is d? So as we can see by this formula, that we have the mod function of this should be a number, which is the message. So if m is equal to 2, then what we have to see is, if we do m to the power e mod n, which is m is the message, which is 2 to the power e, which is already given in this function, which is 3. So 2 to the power 3 mod n we don't have, so n we have to find. Okay, so to find n, what we can do is we have to see another formula, which is ed mod phi n. So phi n is as we can see 3 minus 1 into 5 minus 1, so which is 2 to the power 2 into 4, which is 8. So we can find e with this function, and then we can find n with the c function, and then we can finally decrypt the message. So we can solve this, but it will take time. So the viewers can solve this, and let's then move to the RSA security. Let's see the security of the algorithm. So the security depends on the difficulty of factoring n. So n is phi n. So to compute the function phi n, we use E and D. Sorry, we use P and Q. So to compute the P and Q should be infeasible to find. So one will be 512 bits, the other will be 2048 bits. So the security of the function depends on the difficulty of factoring n, which is to find phi n. So the length of n is equal to pq reflects the strength. The larger the length, the higher the strength. So the 700 bit n factored in 2007 and 768 bit factored in 2009. So this is that. So 1024 bit for minimal level of security today. So at least 1024 bit should be the required length of the numbers p and q to factor phi n. So it is infeasible to solve. Otherwise, it will be highly likely that we can break it. As we can see, we solved this function on our own because the value of p and q were very less. So we will able to calculate, and also we had the p and q values, which usually the attackers will not have. So that is that. So minimum 2048 bits recommended for current usage. The minimum bits required is 124, but 1024, but the minimum security standards bit should be 2048. So NIST suggests 15,360 bit RSA keys are equivalent to the strength 256 bit. RSA speed is quadratic in key length. So let's see the real world usage of public key encryption. So often uses an encrypted symmetric key to encrypt a message M under a public key n, E, generates a new encrypted key K to compute RSA NEK and AES K. So plain RSA does not satisfy Indian requirement, so because it is easy to crack then. So this is the real world usage. So let's see the problems of the digital signature, since it is a digital signature technique. So consider a real life example. When a person pays by credit card and signs a bill, the seller verifies the signature on the bill is the same as the signature on the card. Contracts, they are valid if they are signed. Signatures provided non-repudiation, ensuring that a party in dispute cannot refute and the validity of a statement or contract. So can we have a similar serve in the electronic world? So basically what digital signature does is it checks the, like if we have a debit card and we sign that, so if we see let's take the example as given here only. So let's take a credit card and use that to sign a bill. So the seller will verify that the signature on the bill is the same with the signature on the card. Once we sign the card, it will verify with the signature which is on the, once we will sign the bill, it will verify the signature which is on the card. So once these signatures are matched, only then the transaction has been processed. So it is a real world. But now since we have to use it digitally, what we do is we use a public key and a private key. So with the help of that public key and private key, we encrypt a message. With the help of public key, we encrypt a message and we share the private key to the person receiving it. So once a person receives the private key, he or she can verify the signature which we have done, and if the signature matches, the payment is processed. Otherwise, if an attacker tries to send another private key and if the signature doesn't match, the transaction will not be processed and the person will know that the key is forged. So this is how the digital signature works, and in digital world, so that we don't have to sign it. So that there is that. So this digital signature, one party signature SMAC, one party verifies integrity. So on the one party generates signature, many parties can verify, which is the property of the digital signature which we have to see. So digital signature are what? A digital signature is a data string which associates a message with the same original entity. And what is the scheme called? A signing algorithm which takes the private key, single key, outputs a signature, and a verification algorithm which requires a public key and a message and a signature. So all these uses hash functions. Very often digital signatures are used with the hash function. Hash message is signed instead of the message. Hash functions must be pre-image resistant, weak collision resistant, strong collision. So these are the property of the hash function which I told you in the starting of the video as well, to just make you familiarize with the concept. So RSA signatures. So as we have already seen with this RSA signatures, that we select the two prime numbers, and this is a whole algorithm we have seen before only. So it is just a revision part. So let's do that also. Okay. So what we did was we took two large prime numbers, P and Q. One should be of 512 and one should be of 2048 bit. Then we used that to find the phi function, and the keys generated would be between the range of 1 to that 5 function. Then we compute the keys, and then we got two public keys which are E and N, and one secret key which is D. So what we did was to sign the message. We found S is equal to m to the power e mod n, so which is m to the power d mod n to sign the message. So d is the private key, we used that to sign the message. And when we used what we used to verify the message, we used a public key e and n to verify the message, which is the encrypted message raised to the power e mod n is equal to m. So this was the basic concept of RSA signatures. Hope you liked the video. Thank you so much for watching. Thank you.